So the first programmable logic device that we looked at was the ROM. If you have a ROM, you can implement any combinatorial function using the ROM. Right? And so as we looked at last class, it's very simple. The number of inputs set the number of address lines, right? So this is equal to the number of inputs. K is equal to the number of inputs. And they basically set the number of address lines you have on the ROM, right? So what the decoder is doing is essentially, remember the ROM is made up for decoder and a memory, right? So the decoder is nothing but generating the minterms. And once the minterms are generated for the various input combinations, then that particular combination of the input can give you a multi-output variable, right? So a ROM doesn't make sense if you have only one output you want to generate, because essentially your ROM will have this value of 0 or 1. But suppose you have to generate multiple outputs from which are made up of multiple inputs, then a ROM is a one-shot solution to get you that, right? So the other two devices we're going to look at in this class are called, one is called a PAL, or a programmable array logic. And the second one we're going to look at is a PLA, or a programmable logic array. And what's the difference between the two? So remember, any combinatorial circuit you guys are familiar with. And so any combinatorial circuit can be written as an AND or an OR AND circuit, right? So depending on, if you write it in soft form, you'll implement it as an AND OR. If you write it in POS form, you'll implement it as an OR AND circuit. So what the PAL gives you is, suppose you think there are a bunch of inputs. It gives you the flexibility to program the AND array. So what it has is, and I'll take you through a couple of examples and we'll see how to use these. So basically this gives you the flexibility to change the inputs to the ANDs, right? So you can choose what kind of product terms you can generate from the input. And what it does is, the drawback with this is that it has only a fixed OR array, right? So which means that it can generate only outputs with a certain number of product terms, right? So when you have a fixed output array, remember, this is generating your product and this is generating the sum of products, right? So when you have a fixed OR array, that means that you're limited in how many products you can add. Again, with an example, we'll see how to work this. The other one which gives you more flexibility is the PLA, which has both programmable circuits. So you have a programmable AND network in series with a programmable OR network. So this gives you maximum functionality or maximum flexibility in design. So the drawback between the two obviously is that the PLA is going to be a larger chip, because you've made it programmable for both and OR. It is going to be a larger chip, whereas this chip, because you have a fixed OR array, it is going to be a slightly smaller chip. Again, this is going to be slightly more expensive than the other one, right? So once you add more programming, or if you have the flexibility of adding more programming to your chip, then it's going to increase the cost of the chip. Okay, so let's start with this one because it's the simpler of the two. So let's start with this circuit. Is that we have a chip which you can buy in the market, which allows you to make any number of products and any number of sums for those products, right? So um, let's look at a simple case. So let's look at an example. Through an example, I'll tell you how this structure looks like. So let's look at a PLA. So remember, a PLA, or a programmable logic array, means you have programmable AND followed by a programmable OR. Okay. So let's say we want to implement the following functions. Say we want to implement F1 as the following function, and we want to implement another function, say, right? So this is the function, say, I want to implement. So now let's think about what this programmable chip looks like, right? So what this programmable chip looks like is that, let's first look at the AND array. The AND array, right? Suppose I have four. So let's consider a specific PLA, right, which has four ANDs and two ORs. So in this case, I'm very specific that I have a flexibility of creating four AND products or four AND terms, and I have an option of creating two OR terms, two OR gates. I'll go into detail as to what this device looks like, right? So what does a programmable device in this case look like? So programmable device basically consists of an AND array. So the first level will be an AND array. So I draw a shorthand of an AND array. What does this look like is that the AND array looks something like this. So it has A, let's A prime, B, B prime, C, C prime. And this is generated by taking A, using an inverter to get A, right? Similarly, I have B, take an inverter to generate B prime, and I have C, inverter, and generate C prime, right? So when I draw something like this, what does the shorthand mean? The shorthand means that let's number these gates 1, 2, 3, 4. So the input of the first AND gate, all these six can be made inputs to the AND gate. So the AND gate, what you're doing as a program is, when you're programming this chip, is you're going to pick which of these connections you want to be shorted. So the chip has the flexibility that this AND gate can be treated as a 6-input AND gate, where there are 6 inputs going into the AND gate, right? So you have the flexibility of choosing which input you want to take into the AND gate, right? So, and that is the programming part of this array. So the programming part, obviously, we're not going to go into it, but normally done by blowing up fuses. So it consists of uh, a low melting point metal, and then based on the current you flow in that, you can create a break in the metal. So you can either open up the things you don't want, and so have the remaining of them shorted. So that way what you do is, this is your programmable AND. So everybody following that, this gives you the flexibility of choosing the inputs to the various AND gates, right? So what you have now is, coming out of the AND gates, now I have the OR array. So the way we represent the OR array is, we represent the OR array using the other dimension. So again, this is a programmable OR, right? So what this means is that this OR is connected. There is a possibility that you can connect the OR to all the 4 inputs coming out of the AND. Now, as a user of this chip, you can pick and choose. So let's call this OR gate 1 and this OR gate 2. So in the ideal case, you can connect the outputs of all the 4 AND gates to the input of the OR gate, or you can pick and choose what is the kind of input you want to connect, right? And now certain chips, right? And again, this depends on the PLA. So I'll draw the rest of the chip here. Certain chips have this option where it gives you the option of complementing the outputs. So how do you complement? How do you get a choice for complementing? What gate would you use if I want to complement the outputs? If I want to intentionally complement an output, what kind of gate can I use? Say you, based on a particular signal, if I want to generate A or A prime based on a particular signal, what are the kind of gates I can use? Anybody?
A NAND gate.
A NAND gate. Yes. What other gate can you use?
XOR gate, XOR.
XOR gate. So what typically happens in these kind of gates is you have an XOR gate sitting at the output. And so if you draw the so the XOR gate, again you have the flex. So remember this output X and this output Y is continued. So this circuit I'm continuing to here. So the output of the OR and the AND go into the XOR gate, right? Which has a flexibility where you can either program a 0 or 1 into that particular XOR gate, right? So what you see here is this chip, for example, has gives you a flexibility of picking what are the kind of products you want to generate. Based on the products generated, it gives you a flexibility to pick what kind of sums you want to generate. And then finally, it gives you a flexibility whether you want to send the signal as is or you want it to complement and send the signal out, right? So now let's think about how to implement the first function, which is F1, right? So F1, if you look at it, consists of three product terms, AB prime, AC, and A prime BC, right? So what I would do in this case is I would open up all other circuits and short only. So in this case, the first AND gate I will generate, I will say that this is shorted. So I denote the short with an X, right? And I short B prime. So B prime in this case is this line, right? All other inputs are open. So what this means is that the output I'm generating from the first AND gate is AB prime, right? Similarly, when I want to generate AC, what I would do is I would short this and AC, right? So C is right here. So I would short these two. So the output coming out of this, again, this is one time programmable, right? So again, nowadays we have chips where you can erase the full thing and program it again. But typically, again, it's like the ROM. So you program it once and then you use it for your application. If you want to program again, you have to erase everything. The third the third product term I need to generate is A prime, B prime, C, right? So A prime, B, and C prime, right? So I've generated AB prime, AC, and A prime, BC at the outputs of the three AND gates, right? Now, if I want to generate F1, what do I need to do? Now I need to sum up all these, right? So for the input of the first OR gate, what I'll do is I short this line, I'll short this line, and I'll short this line. So when I short these three lines, it's basically saying that my output of the first OR gate is going to be the sum of these three product terms, right? And then if I want to generate, say, F1 out of here, because this is the true value, I don't need to complement it. So what I'll do is, so if I want to generate the true value out of an XOR gate, what should the other input be, 0 or 1?
Zero.
Zero. Zero, right? So what I'll do is, this is the input for the gate which is generating F1. So I will short it to a 0, right? So this tells me that I'm generating term F1 at the output of the PLA. Now let's look at AC plus BC. AC is already generated here. So when I want to generate BC, I will take B, I will take C. So BC gets generated here, right? And now I want to create my second F2. So F2, what I'll do is, because I have an option of inverting it here, I will choose a 1 here to invert the total sum. And here I'll just pass AC and BC into the gate. So this, by choosing which fuses to blow and which fuses to keep open, I can start with a programmable array and basically get it to generate these two functions. Now, obviously, they are limited in the case that you can't generate any valued function of A, B, and C, right? You have the option that, for example, in this kind of a PLA where you have only four AND gates and two OR gates, this is telling you that the function that you generate has to be at a maximum of four product terms. I can't generate any function which has more than four product terms in its a simplified version, right? And sometimes when you have to generate more than one function, right? Now suppose, so again, what you see here is that this chip gives you the flexibility of only generating 4 product terms. So which means that if you're going to generate 2 functions of these 2 functions should use either all or at least a few of the same product terms. Suppose you had this array, and suppose instead of AC plus BC, I had another input, say AC A prime C prime or something like that, right? If I had that additional sum here, then I won't be able to use this programmable logic. I'll have to find a way. I'll have to find a PLA which has an additional AND gate so that I can generate the number of product terms I need. So whenever you're picking this kind of a chip to implement your function, you need to be very clear about what are the number of AND gates needed. So sometimes, you have to be smart. Sometimes it's not the minimum Boolean expression may necessarily not work. Trying to add a certain term might help you um, implement this faster. For example, if I'd given this expression instead as, if I'd opened up the brackets and written as a plus b into c, the whole prime, and then given you as, a prime b prime plus c prime, if I'd given you something like that, you should be able to see that if I'd given you this as, suppose I'd given this, remember this can be written as a plus b c the whole prime, right? Which can be written as a prime b prime plus c prime. So if I'd given you f2 as a prime b prime plus c prime and f1 as this, right? You would have made, you can also say that, sir, I can't implement this. But what happens is if you simplify this into some of the terms which are included here, you can implement it this way. So you have to also think about whenever functions are given to you, how do you reduce them into terms such that they share as many product terms as possible, right? So the trick in using this is to ensure that share as many product terms as possible, right? So that way you can utilize this chip. Okay. And so how do you express this? So typically we have what is known as a programming table. When you have to design a PLA, you're asked to give what the programming table is. So the way we write the programming table is, so let's take the same example. Now we want to write what is known as the programming table for the PLA. So what we'd say is, we'll take the product terms one by one. So we will take the product term, the inputs. So remember the inputs are A, B, or C. The outputs, right, which are F1 and F2, right? And then I can show in my output, because this chip has the flexibility of generating the true value of the output or the complement value of the output. Below here, I can write if I'm generating the true or the complement. So I can say here that this I'm using the true value of the output. Here I'm taking the complement value of the output, right? So now let's look at remember you have 4 product terms. The 4 product terms are AB prime, AC, A prime B C prime, and BC, right? And so the programming table says that if you take the inputs, the way you generate AB prime is to take the true value of A, take the complement value of B, don't use C. To generate AC, take the true value of A, don't take B, take the true value of C. Similarly, logic for A prime B C prime is take the complement of A, take the true value of B, take the complement of C. And finally for BC, don't care about A, take the true value of B, take the true value of C, right? So this table tells you how you're generating the 4 product terms, right? And now that you've generated the product terms, right, this is your AND array. Now you have to think about the OR array. So in the OR array, we say that to generate F1, I will take the first term in its true value, the second term in its true value, the third term in its true value and not take the fourth term, because my f1 was just defined by these three, ab prime plus ac plus a prime bc prime. Now, because I'm generating the complement of f2, the complement of f2 is generated by taking the true value of ac and the true value of bc. So this is known as the programming table of the PLA. So for the programming table, what you need to identify is what are all the product terms you need to generate. Identify how to generate these product terms by either taking the true value of the input or the complement value of the input. And then how do you generate? So always remember it's an AND first and then an OR. Right? So it's normally the soft form of the expression that you're using. Okay. So how do you define the size of a PLA? Suppose you want to go into the market and look for PLA size. So for a PLA, the size is specified by the following. The number of inputs, right? So this tells you how many variables you can have in your Boolean expression. The number of product terms you can generate. And finally, the number of outputs, right? So again, this is normally written as N, this is written as K, and this is written as M. So if I think about an NKM PLA, what does that mean? It has N inverters, right? It needs N inverters because I need to generate the true and complement value of the signal, right? So for every signal, I need to have an inverter. So it needs N inverters. How many AND gates will it have?
K.
K and
And
A.
how many inputs per AND gate?
N
2n.
inputs.
2N, right?
Two.
Because you have the flexibility of giving either the true or the complement value, right? If you go back here and see, right, you have three inputs here. You have the flexibility of giving either the true or complement value of the signal into the input of the AND, right? So we think about it, we say that it has K to N input AND gates, right? And now what can you say similarly about the OR gates? How many OR gates would it have?
A minus
M.
M OR gates, and each OR gate will have how many inputs?
K.
K, right? So this would be M K input OR gates. Everybody following? Right. So when I write it's an NKM prob. So again, what this tells you essentially is this telling you that if you have n inputs, you need to ensure that if you want to implement any function, that function should be written as it can have a maximum number of k product terms, right? So which means that if you want to implement more than one function, normally we don't use PLAs if you want to implement one function. One function can be implemented using gates. So normally you use this to implement multiple functions at the same time. So when you're doing things like that, remember these are your limitations, right? So when you have to design, when you have to use a PLA, make sure you share as many that's the only trick in solving any question regarding the PLA, is that make sure you share all the product terms, right? So we talk about saying that we say that the programmable AND array is a 2n cross k array, right? That is, they have 2n to the 2 times n inputs, and we have k product terms that we can generate. And similarly, the programmable OR array is made up of k times m. Right? So these are the number of switches you need to think about. So at all times, you have to give information about each and every fuse, whether that fuse has to remain open or closed. If you go back here and see, right, this tells you exactly what each fuse has to be, right? So this is telling you that I need to connect the A fuse, and the B prime fuse to it. See, both the fuses should be open. Similarly, so this is telling you exactly how to short all the fuses in the OR array, and this is telling you how to short all the fuses in the sorry, this is the fuse shorting information for the AND array, and this is the fuse shorting information for the OR array.
Excuse me, sir. What is
Yeah,
this T and C you have written in the brackets?
right. So T means the true. So remember here, if you go here, for F1, we are taking the output of at X, and we are just, because this PLA that I've given you has the option of generating either the true value of the function or the complement value of the function, right? So for F1, what we're doing is whatever is coming out of the OR array, I'm sending it as is to the output. Whereas for F2, because this has an option where I can conditionally invert, right? I can take the output of the OR array and then invert it to get F2, right? So what we are saying here is that the OR array is generating the true value of F1, whereas it's generating the complement value of F2, which means that if you have to get F2, you need to intentionally invert what is coming out of the OR array and then get the true value of F2. Is that clear?
Okay, sir. And one more doubt. Why aren't we including the XOR gates in that NKMPLA count?
Because that's normally option. Not all PLAs have it. So whenever we talk about the PLA time, programming table, we worry only about the AND and OR gates. And this information is got when you give this input. When you give a true and complement, that encodes the information as to how the XOR gate needs to be programmed.
All right. Thank you.
Right. So sometimes you'll see two words being used for these things. They are known as mask programmable, or sometimes you see field programmable. So when you think about PLAs, two kinds of PLA options are available to you, right? So the simplest one that I told you about is field programmable. That is, the chip is available in the market, right? You buy the chip and then you bring it to your lab or bring it to your place of work. You blow the respective fuses and then get your chip to work, right? So there, the fuse blowing is happening in the field. It's happening after the chip is manufactured and come out of the fab. Some foundries also offer what are known as mask programmable. So what they do is they make, so some of you who know how chips are made, um, chips are made using lithography. So it's a mask, a deposition, etch process. So what essentially a mask programmer really means is that these chips are manufactured halfway and they're waiting for the final output from the designer. So once you decide the programming method, the last mask which tells you which fuse is to be blown or not is then manufactured. So the chip when you get from the foundry, in the case of a mass programmable array, already has the programming done onto it, right? So when you buy a mass programmable chip, the programming is already done because you would have contacted the foundry prior to getting the chip in your hands. Whereas a field programmable array happens outside when you buy the chip and then you program it electrically in the lab. So you'll see these words if you start looking into whether it's mass programmable or field programmable. And field programmable are generally used because there you don't have to deal with the foundry. So again, key things you want to remember is reduce the product terms and always remember that minimum function may not always help. So think of a way by which you share the product terms, right? So as I gave an example in the previous case, always remember it's not about minimization in this case. Minimization might end up actually giving you more product terms than you need. So try to figure out how do we express the function such that it shares as many product terms as possible. Okay. So the second one which we discussed was the other version, which is known as a PAL, or programmable array logic. And the difference between the PLA and PAL is that this has a fixed OR array. So you don't have the flexibility of picking how many inputs go into the OR. So here, if you look at your this array, right? This array gave you the flexibility of picking whichever input you want to go into the uh, OR. Whereas what will happen in the PAL is that this will be fixed. It will say that okay, you can give only 3 inputs or 4 inputs to the OR. So the number of inputs to the OR will be fixed. So based on that, you'll have to design the particular function. Right? So let's take um, one example from a textbook. Um, let's look at an programmable array, right? So okay, so let's draw a programmable array. What does a programmable array look like? So as I said, the number of OR gates, you can't have a programming on the number of OR gates. So if you buy, so there is a specific PAL which can look something like this. Right. So what this means is that this can implement only this can implement a function which has 3 product terms or less, right? I cannot implement any function in this PAL which has more than 3 product terms, right? And so now I can think of the AND array as something like this. So this one has 5 inputs, right? Um, Not 5 inputs, it has 4 inputs. I'll talk about the 5th input. So this one has 4 inputs, say. So let's assume the 4 inputs are A prime, B prime. So remember, A prime, B prime are all generated within the chip through an inverter. So in reality, you'll have only 4 input pins, which are going to be A, B, C, D. So I'll talk about the last in a bit, right? So now let's think about a case that you want to implement the function, say, um, let's go back and let's implement a function. Let's say we want to implement a function which is x of ABCD is given by sigma m of 7, 8, 9, 10, 11, 12, 13, 14, 15. So suppose I want to implement this in that first part of the PL. How do I go about doing that? So can somebody tell me what the minimized form of this is? So obviously this is a bunch of minterms, right? And we don't have the flexibility. So you don't see all the minterms. So you have to figure out what are the inputs I need to connect to this function. So can somebody minimize this and tell me what the expression for this is? Remember, A is MSB, D is LSB.
A plus BCD.
Very good. So this can be written as A plus BCD, right? So what you see is X consists of 2. So in the sub form, it consists of 2 product terms. One is A, the other one is BCD. So I can implement it in this. And how would I implement it? I would take, so to generate A, so again, this is your first AND gate. To generate A, I will just fuse A into this input of the AND gate. Nothing else will be fused. For the second, I want to include BCD. So I'll take B, I'll take C. No, sorry, where is C? Oh God, did I mess up? Okay, just a sec. Okay, so let me renumber the. So this is B, B prime, C, C prime, D, D prime, right? So now if I want to generate BCD, so this is my B, this is my C, this is my D, right? So this term I've generated as A, this is BCD, right? The third OR gate, the third AND gate I don't need to use. So see, here is a problem where I have a third AND gate, but I'm not using it. So I will just say that I'm not using this AND gate. And so what I'm getting out here is the function X, right? So I've generated X in this by just programming. So here, again, you don't have the flexibility. So it's similar to the similar to the PLA, only thing you don't have the flexibility of programming the OR array. So now so there is, some PALs have what are known as a return function. So you can buy, certain PALs will have an option where it allows you to take one input and invert it. For example, let's look at this condition.
So fixed or array means the number of inputs are fixed, right?
Number of inputs to the OR are fixed. You don't have the flexibility of choosing what input goes into the OR.
Okay, sir.
So let's look at, so again, this is your programmable AND, this is your OR. So sometimes what happens is some chips give you the flexibility of taking one input here and allowing you to so what it's doing is, if I think of this input as say F2, right? What it's allowing you is you can reuse this F2 back into your array. So it gives you the flexibility. So normally if you look at PAL chips, some chips give you this flexibility and it's normally given to one input, for example. So in this case, if I look at it, it gives this flexibility in F2. Normally it's given in the first, let's take this here, right? And so I have another array which looks like that, right? So let's assume that I have this array, which is basically consists of 3 outputs and 4 inputs, right? And one of the outputs is given, can be treated as an input to the next stage, right? So now, why is this important? So let's take a specific example. Let's assume that we want to generate, and I'll give you a clue. Let's look at this. I want to generate a function W, which is given by sigma m 2, 12, 13. And I want to generate a function Z that is given by sigma 1, 2, 8, 12, 13, right? So can somebody quickly drop the Boolean expressions for these?
So can F2 be used as its own input?
F2, then it becomes an asynchronous design, right? No, generally we don't use it that way.
Okay, thank you.
This is going back to combinatorial. So if you want to make this into an asynchronous circuit, you explicitly do it outside. Don't do it within the PL. Okay, anybody? Boolean value for W?
A prime, B prime, C, D prime plus A, B, C prime.
Very good. C, D prime, sorry. Right. So now what you see now is, if I want to implement Z, right? I see that Z includes W, right? Because 2, 12, and 13 sit in Z also. Now the problem, so basically I can write this as W plus sigma M of 1 comma 8, right? So in this, if I want to implement Z, what I can do is I can implement W in F2. So if I implement W in F2, implement W here, then I can use that W and implement Z in F3. Is that clear? So how would I, so let's quickly implement W. How do you implement W? W, as we looked at, is made up of ABC prime plus A prime B prime C D prime, right? So ABC prime, so it's going to be A A B C prime, A prime B prime C D prime. I won't use this gate, right? So this I've implemented basically. This is ABC prime. This is A prime B prime C D prime, right? So I've implemented W here. Now when I implement Z, right? All I have to do is select W here in my first gate, and my second gate can be minterm 1. What would minterm 1 be? Minterm 1 would be A prime B prime C prime D, right? So A prime B prime C prime D. So that would be my minterm 1. And then my minterm 8 will be what? A B prime C prime D prime, right? So A B prime C prime D prime, right? So this is giving my minterm 1, this is giving my minterm 8, this is giving W. So combine that into, so this helps you sometimes if you need to reuse certain inputs to certain outputs, right? And again, we define what is known as a programming table here. So how do you, so the same logic applies here when you want to do a programming table. So how do you write a programming table for this? Similar as before, this is your programming table. So again, look at the product term and inputs, which are A, B, C, D. Let's call the last one F2. And that's all there is in programming, right? The output really is just a combination of whatever you're doing here. So if you can think of the product terms, if you can break it up, you can break it up as groups of 3, because we know that the output has to be a sum of at the maximum 3 product terms. Right? So if I think of the 3 outputs that I'm getting out of this programming table, so I have 1, 2, 3, 4, 5, 6, and 7, 8, 9, right? Right. So we are not programming the OR array here. The only programming we have to do is for the AND array. So again, if I look at my first 3 product terms, so, and what do these product terms means? These essentially mean these. So I can write 1, 2, 3, 4, 5, 6, 7, 8, 9. Right. So let's code this up into ones and zeros. So if you look at 1, 2, 3, 1 is essentially just taking A. Right. So 1 would be just take A as a true value and rest of them are not connected. Second term would be take B, C, and D and nothing else, right? So the programming table here would be B, C, D, nothing else. The third one, I'm not using it. So I keep all the fuses open. So in this case, my output, what I'm getting is, what did we call this output? X, which is equal to A plus B, C, D. Similarly for 4, 5, 6, let's quickly write. So for 4, 5, 6, I have to give 1, 1 dash, no, 1, 1, 0 dash, right? So my programming table here will be 1, 1, 0 dash dash. My second table is going to be 0, 0, 1, 0 dash. So it is going to be 0, 0, 1, 0 dash. And the final one I'm not using again, right? And so this is generating the output W, which was given by, what was it? A, B, C prime plus A prime, B prime, C, D prime. Again, you can just write it, look at this. And similarly, the third one, when we fill it up, we are reusing this F2, right? So your first fuse is just going to be F2. In this case, I don't blow, I leave all others open, make this one because I'm using the true value. So again, this gives you the flexibility of either using the true value of this input or using the complement of the input, right? So this is, I'm using the true value. The second one again is going to be 0, 0, no, 0, 0, 0, 1. It's the M1, right? So M1 is going to be 0, 0, 0, 1 dash, and M8 is going to be 100 dash, right? And so this is going to give you your expression Z is equal to W plus A prime, B prime, C prime, D plus A, B prime, C prime, D prime. Okay, so this is how you write the programming table for a PLA, for a PAL. So again, when asked, in the exam, we'll give you a bunch of functions and ask you to implement it using either PL or PLA. We'll give you the size, right? So again, the only thing you need to remember in these cases is how do you share? So always remember that the minimized expression may not necessarily give you the best way to implement it. So ensure that you look at all possible ways of looking at the Boolean function, and that will help you implement it in the given size of the PAL or PLA. Okay. All right. So with that, I'll stop the class here, and I'll continue with it on Monday. I'll take any questions you guys might have.
So can you
Sir, can
repeat
you
what you
show
just
slide
said at the
19
end?
once?
Okay. So what I said is, remember, when you're given something like this, right, your hands are tied in terms of how many. So I will tell you, say you have a PAL which takes in 4 inputs, right? And it has 3 outputs where one output can be reused. So that would be how I would say this PAL looks like. And so when I give you the 3 functions, make sure you ensure that you get all the expressions down to a minimum of 3 SOP, right? You don't want to have functions which more, you can't implement in this PAL a function which is written in a form which has more than 3 product terms. So ensure that all the 3 product terms are the same, and then you can do this. So in this case, sharing of functions is not specifically that important, but if you can reuse a particular function, then try and think about that. So when something is given to you in min terms, it becomes easy because you can start seeing, okay, which function is included in which other function, right? But suppose I had given you instead as Boolean um, expressions, then it wouldn't be this easy. In this case, because I gave it to you as a bunch of min terms, you can quickly see that Z includes Y. So I know that I have to use the feedback of Y into Z. But that may not exactly be apparent if I give it to you as a Boolean function, right? So things like that, keep in mind. It's always good to draw K-maps for all the expressions, and then K-maps will quickly tell you whether you've included the function or not, right? So those things you need to keep in mind when you're using these devices.
Right. Thank you.
Yeah.
Sir, can you show slide 19 once?
Just a sec.
Excuse me, sir.
Yeah.
So what does this mean that we don't use an AND gate? Like, do we give it a zero value, or like we just keep it like this?
No, it's not a zero. Now, if you give zero, then the output. So you mean to say in which? By the way, somebody wanted 19. Have you noted on what you wanted to note down?
Yes, sir. Yes, sir.
Yeah. So let's look at this expression, say right here, right? So what we're
Yeah.
when you're drawing something X under the AND gate, all it means is that all I'm saying is that I'm not using that AND gate. That is, all these fuses are essentially open. That's all. So what it means is that this output is going to be high impedance which means it
Okay.
won't really impact what is happening here.
Okay, sir. Yeah, thank you.
So can you explain the 2n into k and k into m for the and and the or is?
Hmm. Okay. So let's think about this. This is a programmable and a programmable OR, right? So if you think about, you had n inputs. When you have n inputs, your chip has the option of giving, you have the option of using either the signal values as is or its complement, right? So the chip generates both signals and its complement. So if I have three signals, three inputs, then I will have six possible um, inputs to the AND array, right? They are basically A prime, B prime, C prime, right? So whenever I think about number of inputs are n, then I will use n inverters to generate 2 times n inputs to the AND gate, right? So once those 2n inputs are generated, the AND gate, the middle term in the NKM expression tells you how many product terms you can generate, right? So this tells you that I have k AND gate. So every product term is generated using an AND gate, and the maximum number of inputs each AND gate has is all the inputs possible using n, right? So hence I can think of the AND array as there are k AND gates. Each AND gate has 2 into n inputs available. So you have to program 2n times k fuses, right? For every AND gate, you have to program 2n fuses. You have to decide whether the fuse has to be open or closed, right?
Okay, so
And
there
so,
will be 2n fuses per and gate. So and since there are k and gates, it will be 2n into k.
correct.
Sure.
And the same logic goes for the OR gate, right? So there are, suppose I'm saying there are m OR gates. That means there are m outputs, which means there are m OR gates, and each OR gate can be connected to a maximum of k outputs of the AND gates. So therefore, I'll have k times m fuses in the OR array I have to think about and program.
Yes, sir. Thank you.
Yeah.
So for the
Hmm.
Compre, can you tell us what the approximate portion will be?
Yeah, I'll few days. I'll discuss with the team and let you know. What do you guys want? Let me ask you the question. What do you don't want to be included?
Sir, so we don't want Verilog.
Verilog, that's fine. That I will. But in terms of Verilog, anyhow, I don't plan to include because it's not essentially.
Yeah, if
It's
it was
not taught in
possible,
class, so it's okay.
so if it was possible, can you leave the last part? Like we didn't get
Arey,
10
how is
days.
that? That is the one I'm not tested, na?
Sir,
I was
memory
hoping that
part.
is easier for you.
So that is easier, but if we don't attend classes, like we have time for Compre now.
So classes now we have hardly 3 classes remaining, and I'm not going to engage all 3. I know that for sure because I'll complete the portion soon.
Oh, okay,
Sir,
sir. Yeah.
actually,
Sir,
we
anything
haven't
is
got
fine as
much
long as the
time.
questions aren't too lengthy.
Okay, I'll keep that in mind.
Yes,
So
sir.
we
Yes,
haven't
sir.
got much
2 hours,
time to
doable questions.
practice.
Okay, yeah, Nishant, go ahead.
Yeah, we didn't get much time to practice asynchronous design. Like,
Hmm.
uh, so even that part, if you could just, I'm not saying exclude it.
That's fine. I'll keep it. So remember that asynchronous design. I have. So one thing I would like to tell you guys. It's fine. You can give all these requests, and I will keep that in mind when we discuss in the faculty team. But remember one thing. Even though I've not covered a lot of topics, it is beneficial for your career that you actually study it yourself, because one of the drawbacks of this semester has been that we have not been able to complete most of the syllabus in courses which you would have completed if you were on campus. So one thing which I hope you guys realize is that you are getting, it's hard for me also as an instructor of the class, because I'm not being able to complete the entire syllabus that I had planned for you. So my hope is that's fine. I'll keep the compre and all. I'll keep all your inputs in mind. But I really wish that you guys don't stop studying, or just study only for the compre is fine for the short term. But you need to keep studying this, or you need to read more if you want to really get a mastery of the subject. Unfortunately, I think this semester I have not been able to ensure that you guys have gotten mastery over the 4 months that I taught you. But I hope you will continue to study what has not been covered in the class and keep improving yourself.
Yes, sir.
Okay.
Sir, I have one more doubt about assignment.
Mm.